two radiologists look at the same X-ray. One flags a shadow as a possible tumor. The other dismisses it as normal variation. Same image, same training, different decisions. Signal detection theory explains why perception is never a simple readout of the stimulus. It is always a judgment call shaped by expectation, motivation, and the cost of being wrong. Signal detection theory, developed in the 1950s and 1960s, fundamentally changed how psychologists understand perception. The theory proposes that detecting a stimulus is not purely a matter of physical sensitivity. It also depends on the observer's decision criterion, which is influenced by expectations, motivation, and the relative costs of different types of errors. A radiologist who fears missing a tumor sets a very different criterion than one who fears unnecessary biopsies. Same sensitivity, different behavior. Signal detection theory organizes perceptual judgments into four categories based on whether the signal was actually present and what the observer reported. A hit is when a signal is present and the observer correctly reports it. A miss is when a signal is present but the observer fails to detect it, perhaps because their criterion is set too conservatively. Misses are the errors that worry radiologists and air traffic controllers, because the real signal slipped through undetected. The other two outcomes complete the matrix. A false alarm is when no signal is present but the observer reports detecting one, a false positive. In medical screening, a false alarm leads to unnecessary follow-up tests and patient anxiety. A correct rejection is when no signal is present and the observer correctly reports nothing. The trade-off between hits and false alarms is at the heart of SDT. Moving your criterion to catch more signals inevitably also increases false alarms. The criterion, denoted beta, is the threshold the observer sets before deciding to report a signal. A liberal criterion means you report signals at the slightest suggestion, maximizing hits, but also maximizing false alarms. A conservative criterion means you need strong evidence before reporting, reducing false alarms, but missing more real signals. Context determines the optimal criterion. A radiologist screening for aggressive cancer should set a liberal criterion and accept more false alarms to avoid missing any real cases. The just noticeable difference, or J&D, is the minimum change in stimulus intensity that a person can reliably detect. Specifically, the change detected 50% of the time. It is also called the difference threshold. Weber's pioneering experiments in the 19th century measured J&Ds systematically across different senses and stimuli, and he discovered a remarkable regularity. The J&D was not a fixed absolute amount, but a fixed proportion of the original stimulus. Weber's law states that the just noticeable difference is always a constant fraction of the original stimulus. This fraction is called the Weber fraction or Weber constant. The formula is delta I over I equals K, where delta I is the J&D, I is the original intensity, and K is the Weber constant for that sense. The constant varies across senses. For brightness, it is about 1 part in 60, for weight about 1 part in 50, and for tone frequency about 1 part in 333. Weber's law has a simple but counterintuitive implication. We do not notice absolute differences, we notice proportional ones. If the Weber fraction for weight is 1/50th, you need to add 2 pounds to a 100-pound weight before noticing the difference, but only 1/50th of a pound to a 1-pound weight. This is why a $5 discount feels substantial on a $10 purchase, but trivial on a $500 item. The discount is the same absolute amount, but a very different proportion. The absolute threshold is different from the J&D. It is the minimum intensity of a stimulus required to detect it at all, specifically defined as the intensity detected 50% of the time. If the just noticeable difference measures change detection, the absolute threshold measures detection from nothing. Our absolute thresholds are remarkably sensitive. On a clear, dark night, the human eye can detect the equivalent of a candle flame 30 miles away. Signal detection theory has transformed how we train and evaluate human performance in high-stakes detection tasks. Airport security screeners, radiologists, and quality control inspectors all face the same fundamental trade-off. More liberal criteria catch more real threats, but generate more false alarms that waste resources. SDT-based training teaches workers to understand their own criteria, and adjust them deliberately based on the costs and benefits of each type of error in their specific context. Weber's law has direct applications in product design, music, and engineering. Audio engineers know that to make a speaker sound twice as loud requires not doubling the volume setting, but roughly 10 times the power output, because loudness perception follows a logarithmic scale governed by proportional sensitivity. The decibel scale for sound was designed precisely to reflect Weber-Fechner perceptual proportionality. Understanding just noticeable differences allows engineers to design controls that feel perceptually linear to users even when they are not physically linear. Perception is never a direct copy of reality. It is filtered through absolute thresholds, difference thresholds, and decision criteria that shift with context, motivation, and training. Signal detection theory and Weber's law are two of the most elegant frameworks psychology has produced, and they explain everything from why radiologists miss tumors to why a $5 coupon feels more valuable on a cheap product.